Welcome to Artificial Intelligence Bytes, the podcast series where we break down the cutting-edge concepts in artificial intelligence for innovators, executives, and tech leaders. I'm your host, and today, in episode 10, we're diving deep into backpropagation in deep learning. Let's explore this foundational algorithm that's revolutionized how machines learn from data. First, let's define the essential concepts. Backpropagation, or backprop, is an efficient algorithm for computing the gradients of a loss function with respect to all weights in a neural network. It works by propagating errors backward from the output layer to the input layer. At its core is the loss function, also known as the error function, a metric like mean squared error or cross-entropy that measures the discrepancy between a model's predictions and actual targets. Gradients are the partial derivatives that show how the loss changes with each weight or bias, guiding necessary adjustments. Neural network layers, including input, hidden, and output, form the structure where backpropagation distributes error terms layer by layer using calculus's chain rule. And for advanced applications, sequence-to-sequence models, or seq-to-seq, rely on backprop to train networks handling paired input-output sequences, such as in language translation. Now, turning to the core principles. Backpropagation is the powerhouse enabling deep learning scalability, efficiently calculating gradients without the prohibitive costs of simpler methods. It begins with a forward pass, where data moves through the network to generate activations and predictions. Next, the error is calculated at the output by comparing predictions to targets, yielding the loss, denoted as either backward pass then kicks in, starting from the output and propagating this error rearward. For each layer, it determines each neuron's contribution to the error and distributes it to preceding layers. This is powered by the chain rule, where the gradient for a weight W in an earlier layer is the product of local gradients along the path, dw equals dy times dy dw, with y being the activation influenced by w. This approach achieves linear time complexity, O, n, by reusing computations, vital for networks with millions of parameters. Once gradients are computed, they're integrated with optimizers like gradient descent to update weights, w new equals w old minus eta times dw, iteratively minimizing the loss. While challenges like vanishing or exploding gradients exist in deeper networks, solutions such as ReLU activations or normalization layers address them, preserving the algorithm's calculus-based error attribution. In high-stakes research and development, this principle allows us to scale models confidently and effectively. To make this practical, consider these examples that mirror real prototypes in advanced labs. Take a simple feed-forward network solving the XOR problem, where the network learns logical operations. In the forward pass, outputs are computed, backpropagation then derives gradients via the chain rule. Using frameworks like PyTorch, you define the model with layers, a loss function like MSE, and an optimizer such as SGD. During training, after calculating the loss, calling loss backward triggers backpropagation, updating weights over epochs to master the XOR logic. Another example is image classification with convolutional neural networks on datasets like MNIST for digit recognition. Backprop sends gradients back through convolutional layers, refining filters to detect patterns accurately. For sequence tasks, like English to French translation in a seq-to-seq model, backprop adjusts recurrent neural network weights based on translation discrepancies, honing the system's linguistic precision. In the real world, backpropagation underpins transformative applications across industries. It's the backbone of machine translation tools like Google Translate, which employ seq-to-seq transformer models trained through backprop to enable seamless multilingual communication in global business. Speech recognition systems in virtual assistants such as Siri or Alexa use it to optimize acoustic models on audio data, ensuring precise transcription for enterprise voice interfaces. In autonomous driving, it trains vision networks to detect objects in real time, enhancing safety in fleet operations. Healthcare benefits profoundly, with convolutional networks trained via backprop analyzing X-rays to identify conditions like pneumonia, driving efficiencies in diagnostics. Predictive models for climate forecasting or biotechnology, such as protein folding in tools like AlphaFold, leverage backprop to accelerate innovation in sustainable technologies. And in foundational AI research, it powers hierarchical feature learning in convolutional and capsule networks, fueling advancements in computer vision and beyond. To summarize the key takeaways, backpropagation is indispensable for deep learning, providing an efficient means to compute gradients through backward error propagation, enabling the training of intricate neural architectures. It relies on the chain rule for optimized, scalable performance, seamlessly integrating with forward passes and various optimizers. Implementation in modern frameworks is robust and intuitive, though mastering error distribution is crucial to avoid pitfalls like gradient instability. Its impact extends from translation and healthcare to autonomous systems, underscoring AI's role in driving corporate and societal progress. Remember, while exceptionally powerful, backpropagation presupposes differentiability, paving the way for exploration into alternatives like spiking neural networks in emerging research. Finally, the mathematical foundation boils down to this key formula for gradient computation using the chain rule, dw equals dy times dy, dw, where E is the loss, y is the activation or output influenced by the weight w. This recursion applies across all layers, ensuring comprehensive gradient calculation. Thank you for joining us on AI Bytes. If this episode sparked insights, subscribe for more episodes, like and share, and visit our channel for the full series. Until next time, stay ahead in the AI revolution.